Okay, this one actually scared me. Number 10. Jezero Crater. You stand on the rim of an ancient lake that has been dry for billions of years. Narrow river channels once fed calm water into this basin. Perseverance rolled across that dusty floor and drilled a core from a rock nicknamed Chayava Falls. The sample, called Sapphire Canyon, surprised scientists by holding odd dark nodules and ringed spots that look like a fossil fingerprint. On Earth, similar patterns often form where microbes change the chemistry of mud and minerals. These mudstones are rich in clay, silica, and carbonates, minerals that are exceptionally good at locking away organic molecules and shielding them from radiation. Instruments on the rover found carbon linked to those patterns and minerals that suggest redox chemistry took place in gentle lake settings. That pairing is the kind of clue astrobiologists spend careers looking for, but the evidence is not proof. Rocks can mimic life. Researchers place the finding on a confidence ladder that runs from curious to convincing. The sealed core has to come back to Earth so labs can run tests that no rover can do. For now, the sample sits in its tube, and the argument over what those spots mean is far from settled. Number 9. Neretva Vallis. A broad valley carved into the rim of Jezero once carried steady water into the lake. This was not a single creek. It was a drainage system that sorted and resorted everything it carried. Coarse pebbles dropped out first. Finer mud rode farther and settled in quiet pools. That sorting built perfect layers for preserving signs of life. Organic molecules and dead microbes get buried fast in fine mud. Clay minerals close around them and form a chemical seal that can hold for eons. Remote sensing shows long, sinuous channels and fan-shaped deposits where water slowed and spread. Those fans concentrate nutrients and build chemical gradients, the exact conditions that microbial communities exploit in terrestrial river deltas. The valley also cut into different rocks and mixed their chemistry, creating pockets rich in phosphate and silica, both of which help preserve organic residue. After the river dried, the story did not end. Groundwater seeped through the buried fan and slowly transformed the mud into a chemical record. That water carried dissolved iron, sulfur, and phosphorus and left mineral fingerprints in the layers. Some of those fingerprints include textures that match microbial mats and biofilms found in ancient sedimentary rocks on our own planet. Scientists talk about targeted drilling along the fan margins and in the fine mud drapes. Only a close sample can tell whether the patterns are biological or just clever mineral chemistry. The most promising parts of this valley may still be buried under a few centimeters of dust. Number 8. Habris Valles Caves. You peer into a dark round hole in the red ground and the world contracts. These are not small pits. They are skylights that open onto hidden rooms carved below the surface. Scientists found them by rechecking old orbital images and spotting shapes that match cave mouths. Some of these skylights are tens to over 100 meters across. The cavities beneath could be several times larger. The chemistry around them is the interesting part. Orbital data show sulfates and water-soluble minerals near some openings and pockets of hydrogen that hint at past water. A cave roof blocks radiation and holds temperatures steadier than the surface. In the driest deserts on Earth, caves shelter living microbes that feed on chemical energy from rock and trace moisture, no sunlight required. Inside a buried Martian room, that same chemical energy would outlast anything on the surface. Iron and sulfur reactions could have sustained microbes, and those microbes would have left mineral mats and microtextures on the walls. The skylights also solve a practical problem. A drone or a tethered sampler could drop straight through the hole and into protected sediment layers. That kind of direct access is rare on Mars. No mission has gone in yet. The caves sit dark, sealed by their own roofs, with whatever chemistry they hold still untouched. Number 7. Nili Fossae, a system of concentric grabens, crustal blocks that cracked and sank when the Acetes impact shook this part of Mars roughly 4 billion years ago. The fractures stretch across hundreds of kilometers along the northwestern rim of the Acetes Basin. Some of these trenches drop half a kilometer into ancient rock. But the fractures did something useful. They cut deep enough to expose rock that had been buried since the earliest days of the planet. The Mars Reconnaissance Orbiter mapped one of the most diverse mineral collections anywhere on Mars across a region spanning roughly 30,000 square kilometers. Olivine, iron and magnesium smectite clays, hydrated silica, kyalinite, serpentine, and carbonates, all sitting side by side in the same broken terrain. Olivine reacts with water and heat to produce serpentine and hydrogen through a process called serpentinization. That reaction powers microbial ecosystems in deep ocean vents and underground fractures on Earth where sunlight never reaches. The carbonates found here in 2008 were a milestone because they form in neutral to alkaline water. the kind of gentle chemistry that preserves organic molecules and gives microbes a stable home. Then there is the methane. Telescopes and orbiters have detected seasonal plumes near Nili Fossae. Methane can come from geology or from biology. Either way, something active is happening below the surface. If subsurface water is still reacting with olivine-rich rock, that reaction could be feeding simple life right now. Or it could be preserving ancient traces of organisms that thrived here when Mars was younger. Clays plus carbonates plus serpentine plus methane in the same fractured landscape. Astrobiologists rarely see that convergence anywhere, let alone in one place. Nili Fossae was a serious candidate landing site for Perseverance before Jezero won out. The two sites sit next door to each other and share geological roots. What Nili Fossae holds in its exposed fracture walls is still an open question. Number 6. Gale Crater. Deep below Gale, groundwater once soaked layers of sand that are now dry rock. Curiosity found signs of that hidden water in ancient dunes and in mudstones further down in the basin. When groundwater rises through loose sand, it leaves behind minerals like silica and manganese oxides. Those minerals lock organic fragments into a hard matrix and protect them from radiation. Curiosity also measured organic molecules and unusual manganese signals. Manganese chemistry often tracks with changing redox conditions driven by life or by oxygen-free reactions that life can exploit. The distinction matters because surface lakes can dry in a few thousand years. Underground flows can keep pockets wet for millions. Those pockets become isolated chemical worlds. Curiosity measured organics mixed with manganese and silica in places that were clearly soaked from below, not from surface rain. To find more of them, you map where the dunes were wet, use radar that reads layers beneath the surface, and pick the soft, fine beds that trapped organics fastest. Then, you drill in small steps and keep everything sealed. That approach produced the first real clues from Gale. It also taught a harder lesson. Mars buries its best evidence deep and mixes it with tricky chemistry that can fool you. So scientists combine many signals at once. Textures in the rock, mineral pairings, organic chemistry. Pattern matches that only make sense together. If all of them line up, a purely non-biological explanation starts to look unlikely. Number 5. Eridania Basin. About 3.7 billion years ago, a basin in the southern highlands held one of the largest bodies of water Mars ever had. Scientists estimate it contained roughly 210,000 cubic kilometers, about 9 times the volume of all the Great Lakes combined. This was not a shallow lake. Parts of that sea were between 500 and 1,500 meters deep. In 2017, NASA-funded researchers used the Mars Reconnaissance Orbiter to study thick deposits sitting in what were once the deepest parts of that water. The deposits are over 400 meters thick. The spectrometer identified saponite, talc, serpentine, carbonates, and iron sulfides in those layers. That exact mineral package forms at hydrothermal vents on the ocean floor, where hot water rises through cracks in the crust, reacts with rock, and builds thick mineral deposits around the vents. Those vents are where many scientists believe life on Earth first took hold. The Eridania Sea existed at roughly the same time as the oldest evidence of life on our own planet, around 3.8 billion years ago. A deep, warm, Martian sea with volcanic heat pushing mineral-rich water through the floor would have been remarkably close to the conditions that gave rise to biology here. Depth gave this environment something that lakes and rivers could not. Stability. A deep sea buffers temperature swings. It shields the floor from radiation and surface storms. Hydrothermal vents provide chemical energy without sunlight. Microbes that metabolize sulfur and iron could have thrived in those dark, warm fractures for millions of years, and the mineral deposits around them would have entombed whatever they left behind. The deposits are still visible from orbit across several subbasins in the Eridania region. No rover has visited. Scientists have called these deposits a new category of astrobiological target, distinct from anything explored so far. A fossilized deep sea hydrothermal system with the right minerals, the right age, and the right thermal history. If Mars ever had its own version of life's origin, this ancient ocean floor is where the evidence would be thickest. Number 4. Idaeus Fossae. A tangled maze of ancient valleys cuts across the old crust like a buried river web. These channels fed large drainage systems and carried sediment from highlands into low basins. Where fast water slowed, it dropped heavy sand first, then fine mud that sealed and preserved whatever organic material had been carried along. Junctions and abandoned meander belts are the targets. Orbiters show branching channels, stacked fans, and clay-rich patches that point to long-lived flow. Chemical gradients form naturally where different rock types mix. and those gradients tend to host the most diverse microbial communities wherever liquid water exists. The mineral maps from orbit show where silica, carbonates, and sulfates gathered along the valley margins, creating chemical environments that would cage organics and hold them in place. The practical plan is straightforward. Land where the layers stack best. Drill shallow into the fine mud drapes and into paleosols along the fan edges. Use microscopes and chemistry tools to read tiny reaction fronts and nodules. Look for organic compounds, for mineral pairs that only form under biologically influenced chemistry, and for textures that match microbial mats. If multiple independent lines of evidence agree, the case gets hard to dismiss. Ideas Fossae offers something most sites cannot. Not a single promising outcrop, but a wide network of layered deposits, each one a separate record that may cover millions of years of Martian history. Number 3. Bright Angel Formation. Perseverance drove into a rust-colored band of rock partway up the crater wall and found something the mission planners had not expected. The Bright Angel Formation sits at a geological boundary. Below it are older rocks that record an early period of hot, acidic water. Above it, the chemistry shifts. The water that soaked these layers was calmer, more neutral, the kind of environment that biology could actually tolerate. That transition matters more than any single rock sample. It records the moment when Jezero's water chemistry changed from hostile to habitable. Small dark nodules and pale rings pepper the rock surface. They formed when water moved through mud and altered iron and sulfur minerals in place. Clay and silica in the surrounding matrix then closed around whatever organic molecules were nearby and held them. The Sherlock and Pixel instruments on Perseverance mapped organic carbon sitting in the same tiny zones as those iron-sulfur nodules. In shallow lake sediments on Earth, that pairing often appears where microbial communities drive redox chemistry. The formation also records more than one wet period, which means these rocks were not soaked once and abandoned. Water returned, reworked the chemistry, and left additional mineral layers. The rover instruments can flag a signal, but they cannot measure the molecular detail. The confirmation requires clean labs, mass spectrometers, and contamination controls that only exist on Earth. The sealed cores drilled here will either reinforce or collapse the biological interpretation. Until those tubes are opened, the Bright Angel Formation sits in a strange middle ground, too interesting to ignore, too ambiguous to celebrate. Number 2. Gusev Crater. Spirit rolled into this basin expecting flood basalts and found a surprise in the Columbia Hills. Patches of glassy, silica-rich rock that looked like the residue left by hot water. Similar deposits form at hot springs and geysers on Earth, and they are among the best environments on the planet for preserving microorganisms. Silica precipitates around microbial cells, hardens into glass, and locks their shapes and chemistry inside. Spirit also found sulfur minerals and veins that recorded hot fluids moving through fractures. Small hydrothermal systems, fed by volcanic heat and groundwater, once ran through these hills. Energy from heat, liquid water, and mineral chemistry that embalms whatever it touches. That is the combination origin of life researchers look for when they study how biology might start on a rocky world. The search strategy at Gusev is specific. Target the glassy center layers and the mineralized margins where hot fluids met cooler rock. Collect thin chips from the glassy surface and from the deeper altered rock beneath it. Look for organic fragments trapped in the glass and for tiny structures that match the laminated mats that hot spring microbes build. Mineral context, organic chemistry, and microscopic textures all have to point the same direction before the case holds. Spirit's mission ended in 2010 when the rover lost power in Martian winter. The Columbia Hills have been quiet since, but the silica deposits are not going anywhere. They have been sitting in the same spot for over 3 billion years, and they will still be there when the next mission arrives with better instruments and the ability to bring samples home. Number 1. Lefroy Bay, Otis Peak, Bills Bay. 3 small patches of ground that would be easy to drive past if you did not know what the minerals meant. Orbital maps and Perseverance observations show high concentrations of silica, phosphate, carbonates, and manganese oxides in these spots. Each mineral does a different job in preservation. Silica encases organic molecules in a glassy matrix. Phosphate, a building block of DNA and cell membranes, tends to persist in buried sediment long after softer compounds decay. Carbonates trap carbon and lock it into mineral lattices. Manganese oxides form under changing redox conditions and frequently appear where oxygen or biological activity altered the water. The Pixel instrument flagged carbonates at Bills Bay. Perseverance found silica-rich rock at Lefroy Bay and phosphate-rich material at Otis Peak. That combination in a single traverse is unusual. Paleontologists working on early Earth would treat a site with that mineral spread as a high-priority target because each mineral preserves a different category of evidence, and together they cover gaps that any single mineral would leave. The next step is precise sampling. Tiny, uncontaminated chips taken from the exact mineral layers. Context matters. Where the chip came from, which grain it touched. That information determines whether an organic fragment is ancient or a modern contaminant that hitched a ride from Earth. Rover instruments can point the way by mapping minerals and flagging textures, but the final word comes from labs where mass spectrometers separate signals that no rover can untangle. Carbon fingerprints, molecular weights, isotope ratios, and microscopic structures that only biology produces. Multiple methods have to agree before a hint becomes evidence. These 3 bays may be small patches on a big planet, but the chemistry packed into them is dense, varied, and exactly the kind that rewards careful, patient work.